Welcome back students. Chemical properties of alkali metals. In this video we are going to study that what are the different reactions shown by alkali metals. That means how do they react with oxygen, acids, water, and how do they dissolve in liquid ammonia. We'll study all these in very detail in this video. Let's start. Chemical properties of alkali metals. Okay, actually the alkali metals are highly reactive metals and their reactivity increases down the group. Now why they are very reactive? Because low value of first ionization enthalpy. What are metals? Metals are those which release electrons, and more easily it will release electron, more would be its reactivity. So the low value of first ionization energy, that means it is very easy to remove an electron, that's why it is very reactive metal. So these are reactive metals. And why it is very easy to remove an electron? Because its size is large. So the first reason is low value of first ionization enthalpy, which is due to larger size. The next one is low heat of atomization. And what is heat of atomization? It is the amount of energy required to remove an electron. It is amount of energy to break down the bonds of a molecule to make the free atoms. Just see, we have let's say nitrogen. We take example of nitrogen. We have N2. So if we want to break this molecule N2 molecule into nitrogen atoms, in that case the amount of energy required would be the energy of atomization or heat of atomization. So in case of alkali metals, they are highly reactive, and the reactivity is due to, yes, it is due to low value of first ionization enthalpy, which is because of large size, and which is due to low heat of atomization. Reaction with oxygen. Alkali metals, when burned in air, form different kind of oxide. Obviously we know when something is burned in air it forms oxide, but alkali metals form different type of oxides. Some form peroxide, normal oxides, peroxides, and superoxides. For example, the alkali metals on reaction with limited quantity of oxygen, they form normal oxide of formula N2O. In case of sodium it would be Na2O. In case of lithium it would be Li2O. Simple oxides. And this is the general reaction. Now when heated in excess of air, there are three possibilities. First is formation of normal oxide, in which oxygen is in 2- form. Second possibility is formation of peroxide, and the third possibility is formation of superoxides. So when heated in excess of air, lithium forms normal oxide. It does not form peroxide or superoxide. Sodium form peroxide, while rest of the lower elements or higher elements of the group form superoxides. So what we see here, that the reactivity of alkali metals with oxygen and also the stability of peroxide and superoxide increases down the group. As we move down the group, the tendency to form peroxides and superoxide increases. Lithium only forms normal oxide, sodium forms peroxide, rest of them forms superoxide. So we can say that down the group the tendency to form peroxide and superoxide is increasing. And what is the reason for this? That as we move down the group, the size of ion increases. Therefore, larger cations are stabilized by larger anions through higher lattice enthalpy. The size of actually peroxide and superoxide oxides, the oxygen part, is larger. So a smaller metal ion or cation, let's say if we have small cation, it cannot accommodate large anions. More than 2 it cannot accommodate. So but if we have a large cation, this can easily handle large number of larger anions. So larger anions are stabilized by larger cation, and in down the group we know that size of cation increases and because of which the stability of peroxide and superoxide also increases because they are large in size. Next is reaction with hydrogen. Alkali metals react with dry hydrogen, that means hydrogen which is free from moisture, about 673 Kelvin to form colorless crystalline hydrides, that means they are solid. All the alkali metal halides are ionic solids with higher melting point, and this is the general formula. That means if we react sodium, if sodium reacts with hydrogen, the reactivity would be like this, 2 here, and it will form NaH. Similarly, lithium would form LiH. These are alkali metal hydrides which are formed when alkali metals are reacted with hydrogen. And there are some special features of hydrides, and the first is that the stability of hydrides decreases down the group from lithium to cesium. And why? It is because of the fact that MH bond, that means metal and hydrogen bond, that means in case of lithium it is LiH bond, in case of sodium it is NaH bond, in case of cesium it is CSH bond. This bond becomes weaker due to increase in size of the alkali metals. It's very obvious that, let's say, if the size of metal is large, we know that the size of hydrogen is fixed. Now, this was the one case. In another case, let's say cation is small, metal and also hydrogen is small. So here we can see that the bond length is larger as compared to this. So larger the bond length, weaker would be the bond. So that is why as we move down the group, the size of metallic cation increases, and thus the strength of bond decreases, or the stability of alkali metal hydrides also decreases. Now these hydrides react with water to form corresponding hydroxides, and hydrogen gas is released. So this indicates that, okay, what is happening? Lithium hydride is reacting with water to form an alkali and hydrogen gas. So these hydrides are strong reducing agent. These are strong reducing agent, and their reducing nature increases down the group. Alkali metals also form complexed hydrides. Not those were the simple hydrides, they also form complexed hydrides such as lithium aluminium hydride, and these two are the catalyst, a well-known catalyst used in organic chemistry for different conversions, and these are also good. They are basically used for reduction. They are good reducing agents, so they are used to carry out organic reductions. All these hydrides, means all the hydrides of alkali metal, react with proton donors such as water, alcohol, gaseous ammonia, and alkynes liberating H2 gas. They react wherever they find a proton donor, that means they act as base. When there is a proton donor like water, alcohol, they also can donate proton, or we know terminal alkynes are also acidic. So they react with those molecules which can donate a proton, and they liberate hydrogen gas. So this is the reaction with alcohol, this is with ammonia, and this one is with terminal alkynes which are acidic. Now this order of reactivity of alkali metals toward hydrogen decreases as we move down the group, as we have discussed, because the stability of hydrides decreases. And this is because the lattice energy of hydrides decreases. Lattice energy is directly related with the stability of compound, as we have discussed that most of the alkali metal hydrides are ionic in nature, and their stability decreases down the group. That means their lattice energies decreases down the group as the size of metal ion increases. Next is reaction with matter. This is an interesting reaction that the alkali metals have large negative reduction potential, as we know, so they can act as better reducing agent as compared to hydrogen. Alkali metals, when react with water or other compounds containing acidic hydrogen atoms, such as hydrogen halides or acetylene, again ethylene molecule, terminal alkynes, they liberate hydrogen gas. Just like this, sodium is reacting with water to form NaOH and liberating hydrogen gas. Again with HCl, it also liberates hydrogen gas. And this reaction becomes more and more violent down the group. That means the reactivity of metals, as we know, we have studied it very starting, that reactivity of alkali metals increases down the group. That means this reaction becomes more and more violent as we move down the group. Lithium reacts very gently, while sodium starts, it melts on the surface, it starts floating on the surface of water, and sometimes it also catches fire. Why? Because it reacts with water, it liberates hydrogen gas. Because of this hydrogen gas, it starts floating on the surface, and this is an exothermic reaction because of heat is also involved. There is hydrogen gas, there is heat, so it sometimes starts burning. While potassium and other elements also react very vigorously and they catch fire on the surface. Let's see this. Let's take this example. This is a reaction. This is a demonstration of the reaction in which sodium is put on the surface of water, and let's see what happens. It starts floating on the surface. Hydrogen gas is liberated and it catches fire also sometimes. Next is reaction with halogens. Alkali metals react vigorously with halogens to form metal halides on general formula Mx. We know a very common halide of alkali metals is sodium chloride, which is used as table salt, and they are mostly crystalline solids like this. This is the common reaction. And reactivity of alkali metals for particular halogen, we know it increases down the group from lithium to cesium. And again, the reactivity of halogen is from fluorine to iodine. Fluorine reacts more vigorously than chlorine, and then bromine and so on. So we can see here is sodium, let's say 2 sodium reacts with Cl2 to form NaCl. Similarly, sodium would also react with fluorine to form, it would be 2 molecules of NaCl, it would be 2 NaF, but this is very fast reaction. It is so fast that it cannot be controlled. Now, solubility of alkali metals in liquid ammonia. It is an important property of alkali metals that when all the alkali metals get dissolved in ammonia and they result in formation of deep blue color solution. When alkali metal is dissolved in ammonia, it becomes blue in color. The solution becomes blue in color. Now, and also these blue solutions of alkali metal in ammonia are highly conducting in nature. Now why? Because these solutions contain ammoniated cations and ammoniated electrons as shown below. Let's say we have sodium, we dissolve sodium in ammonia, so it results in formation of Na positive ions, ammonium ion are here, electrons are released and ammonium ions are here. So this was the general formula. Let's say this was y, so if we take 2 there would be 3 and so on. Okay, so this is the general expression. So what we can see here, there are ammoniated metal ions and also ammoniated electrons, and these two are the main reasons that why liquid, this solution is blue in color and why this conducts electricity. So this was blue color of the solution is obviously due to ammoniated electrons. These electrons absorb energy. They are and they undergo transition which results in emission of electron in visible region, and which is actually of blue color, and that's why the solution is blue in color. The blue color solution is considered to be due to ammoniated electrons which absorb energy corresponding to the red region of the visible light, and their excitation to the higher energy level, the transmitted light is blue, which imparts blue color to the solution. That means the blue color of solution is basically due to the transition of these ammoniated electrons, which result in release of the light of blue color. While the electrical conductivity is due to both electrons as well as ions. So there are two main properties. The first is that solution is of blue color. It is blue in color because of ammoniated electrons. Secondly, it conducts electricity. So this conductivity is due to both ammoniated electrons and ammoniated cation. They both participate in conductivity. The blue solution on standing slowly liberates hydrogen and result in formation of amide. You can see this reaction. These metals are dissolved in ammonia, which result in formation of ammoniated ions, ammoniated electron, and slowly they liberate hydrogen to form metal amides. When the concentration of these ammonium solutions in which ammonia is metals are dissolved in ammonia, when the concentration is above 3 m, that means 3 mole per liter, when the concentration is above 3 mole per liter, the solution of alkali metals in liquid ammonia basically becomes copper bronze color rather than blue. In small concentrations, it is blue in color, but when the concentration is above 3 m, 3 mole per liter, the solution becomes of copper bronze color. And this is because these solutions in which the concentration of alkali metals is about 3 m, they contain cluster of metals ion. There are lots of metal ions which are present in form of clusters, and hence they produce metallic luster of copper bronze color. The blue colored solutions are paramagnetic, obviously because of presence of free electrons, but the bronze solutions which are formed due to cluster of metal ions when they are present in concentration more than 3 m are actually diamagnetic due to formation of electronic cluster in which ammoniated electrons with opposite spin group together. So this is a special and interesting fact that when metal ions, alkali metals are dissolved in ammonia in small amount, they are blue in color, but when the concentration is more than 3 m, they becomes of copper bronze color. This is because those all ammoniated ions come together and they form a cluster, and previously the blue solution was of paramagnetic because of presence of unpaired electrons, but now the bronze colored solution is diamagnetic as all the electrons are present are in the form of cluster and the opposite spin electrons group together. And these solutions are hence the copper bronze solutions hence are strong reducing agent than hydrogen also, and hence they react with water to liberate hydrogen. Now reaction with sulfur and phosphorus. Alkali metals react with sulfur and phosphorus on heating it to form sulfides and phosphorus respectively, and this is the general reaction of sodium with sulfur. Sodium sulfide is formed, and this is the reaction with phosphorus. Sodium phosphide is formed. Next is reaction with mercury. Alkali metals combine with mercury to form amalgams. Amalgams are basically alloys in which one of the element is mercury. Now these reactions are highly exothermic in nature, and this is how sodium reacts with mercury to form sodium amalgamate, and a large amount of heat is released. These are exothermic reactions. Next is salt of oxo acid. What is an oxo acid? An oxo acid is a compound which contains oxygen. It has at least one hydrogen atoms which is attached to oxygen, that means it is acidic proton. Next, it contains at least one atom other than oxygen and hydrogen, and it has a hydroxyl group, and hence it has a hydroxyl group and an oxo group, and both are attached to the same atom. And here are some examples. The first is carbonic acid. Let's see what is the structure. The structure is basically this. for carbonic acid. Okay, it contains oxygen. Yes, it contains oxygen. It has at least one hydrogen atom attached to oxygen. Yes, it has in fact two hydrogen atoms attached to oxygen. It contains at least one other atom. Yes, it contains a carbon atom. And both hydroxyl group and oxo groups are attached to the same atom. Is it so? Yes, this is the oxo group attached to carbon, and these are hydroxyl group attached to the same carbon. So this is an oxo acid. Similar is the situation with sulfuric acid, which has this structure, which satisfy all the criterias. And so is H3PO4. Now, salt of oxo acids are prepared by reaction of alkali metal with these oxo acids. And salt of oxo acids are soluble in water, and they are thermally stable. When they are heated, they do not decompose. Like carbonates. Carbonates have general formula M2CO3. Sodium carbonate would be Na2CO3, and sodium hydrogen carbonate will be NaHCO3. These are highly stable to the heat, so that means the salts of oxo acids of alkali metals are generally stable to the heat, and they are soluble in water. There is an exception, that lithium carbonate is less stable to the heat. And why? Because of, we know, anomalous property of lithium, because of which the size of lithium positive ion is very small, because of its polarization of large ion formation, more stable, Li2O and CO2. So this is an anomalous property of lithium, that its carbonate are not stable to the heat, while in generally all the alkali metals form the carbonates or hydrogen carbonates which are stable to the heat. And next is that lithium hydrogen carbonate does not exist in solid form, while rest of them exist in solid form. Next is that stability of carbocations and hydrocarbonates. These are carbonates and hydrogen carbonates. Stability of carbonates and hydrogen carbonates of alkali metal decreases down the group, and this is because the electropositive character of metal increases down the group. So lithium hydrogen carbonate is actually that shows that is almost unstable. It does not exist in solid state. Sodium hydrogen carbonate or sodium carbonate are more stable as compared to lithium hydrogen carbonate or lithium carbonate, and further going down the group, the stability will keep on increasing. Like potassium hydrogen carbonate would be more stable than sodium hydrogen carbonate. So down the group, the stability increases. Stability of carbonates and hydrogen carbonates increases down the group due to increase in electropositive character. So here is a solved problem, that alkali metals radially dissolved in liquid ammonia to give blue colored solution. Just we have discussed that when alkali metals are dissolved in liquid ammonia, they result in formation of a blue colored solution. So it is asking that what is the reason for this. And just we have studied that this blue color of the solution is due to ammoniated electrons. These ammoniated electrons absorb the energy in red region, they undergo transition, and then when they come back to their ground state, they result in this extra absorbed energy in form of radiation, which comes in blue color of the visible light, because of which this solution appears to be blue. So the answer is ammoniated electrons. Next is, choose the compound which does not possess peroxide group. So actually oxides are of three types. First is simple oxide, and these contain O2 negative ions. Next are peroxides, and these are generally O2 2 negative ions. And next one are superoxides. Actually these are superoxides, and these superoxides contain O2 negative ions. So we have to find out that which one of these four does not contain a peroxide ion and which is not a peroxide. Okay, So in this, if we find out the oxidation state of O2, what we find, we know that of sodium is +1, so it would be 2 plus 1 plus, let's say, x is equal to 0 or x is equal to -2. So here it contains O2 to negative, so it is a peroxide. Next is this compound, chromium pentoxide, and the structure of this is actually like this. A chromium in the center, an oxygen here, and 4 oxygens at these corners, and which are bounded in this form. So if you see, these are actually nothing but O2 to negative. So it contains oxide ions. So it contains peroxide ions. So it is also a peroxide. If we see this barium dioxide, we know this is a alkali earth metals, the group 2 elements. It would be +2 plus, let's say, for oxygen it is x0 or x is again -2. So it also contains O2 to negative ion. So it is also a peroxide. Let's finally talk about Fe2O3. The structure of this is like Fe connected to oxygen from this side, another iron connected to oxygen this side, then oxygen. Here you can see there is no this radical. It does not contain any peroxide group, so it is not peroxide. So the correct option here is C. Fe2O3 does not contain peroxide group. Students, in case you have any doubt in this topic, you can post that question in our discussion board. For that, all you need to do is to go to the home page of askIITians. There you will find an option of discussion board. You have to click there. Then in the right side, you will find a portion of Ask Experts. In that, just select the category in which you want to post your question. Let's say it's physical chemistry. Then post your question here, and then if you want to attach any image, use this option to attach the image, and finally post it by clicking on Get Answer, and you will be answered within 24 to 48 hours by our experts. So students, now we know that alkali metals show all the reactions which are typical of any metal. They react with water to replace hydrogen, and the reaction is very violent actually. They react with acids, they react with oxygen to form basic oxides. We know their hydroxides are also basic. So in this video, we studied about all the chemical properties of alkali metal. One important thing which we came to know is that alkali metals dissolve in liquid ammonia to give deep blue color solution. In next video, we'll move to some common compounds of alkali metals. Thank you.